Welcome back. Let's begin this lecture with this problem on the page. Consider the angle theta whose terminal side passes through the point 4, 3. Find the values of the 6 trigonometric functions of the angle theta. This is a very standard wording, and the question is, what are we supposed to do with it? Well, we have a point 4, 3. And so the unit circle has a radius of 1. So if we sort of zoom out and look at the xy coordinate system, perhaps 4, 3 would end up somewhere over here. So evidently what we have is an angle theta in the standard position whose terminal side is going to pass through this point. And I suppose the terminal side will actually keep going. And the angle theta in here is the angle we're supposed to be using. So what we did last time was effectively draw a straight line from this point down to the x-axis and say this is a right triangle with side lengths 4 and 3. Now, if we wanted to find cosine of theta, right? Cosine of the angle theta should be the x-coordinate in the unit circle. So it would be incorrect for us to say that cosine theta is equal to the x-coordinate 4 because this point is not the intersection with the unit circle. What would be correct is if we took this triangle and we took a similar triangle right in here, and we considered the point of intersection there and found the side lengths there and there. So the way we're going to do this is going to say 4 squared plus 3 squared is 25, which makes the hypotenuse of this triangle 5. But in order to fit it inside the unit circle, we need to shrink the entire triangle by a factor of 5. So to get to, I suppose, 5 divided by 5 equals 1, then we would have to write here 3 divided by 5 and 4 divided by 5. So the point of intersection right there would be 4/5, comma, 3/5. And then we could quickly say that cosine of the angle theta, the x-coordinate in the unit circle, is 4/5. Then sine of theta, the y-coordinate in the unit circle, is 3/5. And then tangent of theta, which is sine of theta divided by cosine theta, is going to be 3/4. And then for the reciprocals, we just say secant of theta is equal to, the reciprocal of cosine is 5/4. Cosecant of theta, the reciprocal of sine of theta, is 5/3. And finally, cotangent of theta, the reciprocal of tangent of theta, is 4/3. And we have successfully evaluated the 6 trig functions of the angle theta. All right, let's look at a similar idea. Let's consider a new angle phi whose terminal side passes through the point -12, 5. And this is going to be in the second quadrant. Our goal is to do the same thing, find the values of the 6 trig functions of that angle. So to get a visual for angle phi, I'm going to put a measurement on the screen. We're not interested in the exact angle measure of phi. That's not what we're after here. We're just trying to build a conceptual understanding. So I'm going to move this out of the way. The green thing right there, that indicates the angle phi in standard position, counterclockwise from the positive x-axis. So if we try to do something silly, like make a segment from this point down to 1, 0, like we did before, we get this ridiculous obtuse triangle. And this is not going to be helpful when we try to do right triangle trigonometry. But instead of connecting it there, what if I made the triangle straight down to the negative x-axis? Now I have a right triangle with an acute angle inside, and I can do all the same things. Let me demonstrate what we mean. So here we have a right triangle. Technically the angle phi is out here, but we have a side length of 5 and a side length of 12 with a right angle here. So if we were to label the hypotenuse c, we could say c squared is equal to 12 squared plus 5 squared. That's 144 plus 25 comes out to 169, which means c has to be 13. Now, if we want to take this and we want to shrink it down to fit inside the unit circle, we would make a triangle similar to that, but much smaller. Specifically, we would take the hypotenuse and shrink it 13 times so we get 1. And that would fit right here inside the unit circle. So then if I shrink each of the side lengths by a factor of 13, then those are going to be the side lengths corresponding to this point, which should have coordinates. Let's test this. Geometry, I'm going to place a point with coordinates, and I'm going to say negative 12/13 for the x coordinate and positive 5/13 for the y coordinate, and see if that falls right on the unit circle. Get the label out of the way, and it does. That's our point right there. Perhaps a little bit hard to see because of the size. But the moral of the story is we can then take that point, which, to sketch a unit circle now, the angle phi would extend this way, and this point would have coordinates negative 12/13, comma 5/13. And we could say sine of angle phi is the y-coordinate 5/13. Cosine of angle phi is the x-coordinate negative 12/13. And then tangent of phi is sine of phi divided by cosine of phi, which is negative 5/12. Then the reciprocals, cosecant of phi, the reciprocal of this, is 13/5. Secant of phi, the reciprocal of cosine of phi, is negative 13/12. And finally, cotangent of phi, the reciprocal of tangent of phi, is negative 12/5. And there we have all six. All right, now let's fully generalize this. So if we have an angle theta, which I've arbitrarily drawn to be in the fourth quadrant, but this theory is going to work for any angle theta, and the terminal side passes through a point x, comma y. What we want to do is make a right triangle by connecting that point to the x-axis to form a right triangle, and then we note that this right triangle has legs of length absolute value x and absolute value of y. So then we can use the Pythagorean theorem to say, if I declare the hypotenuse to be r, then r squared is equal to the absolute value of x squared, which is just regular x squared, and then the absolute value of y squared. If I square root both sides and declare that r needs to be positive, then I get an unambiguous square root of x squared plus y squared. I'm going to go ahead and do that here. And this is just a choice we make to make things sort of easier to conceptualize. Now, if I want to find sine theta, cosine theta, tangent theta, so on and so on, I need to first get this triangle shrunken to fit inside the unit circle. Okay, so to shrink the hypotenuse, I would have to take the hypotenuse and divide by itself, so now the hypotenuse inside the unit circle is 1, which means these sides of the triangle right here are going to become the absolute value of x over r and the absolute value of y over r. Now, when I go to say the sine of angle theta, it's not just the absolute value of y over r. I have to look at the direction. Because we're in the fourth quadrant, we're going to go below the x-axis, so the y-coordinate is actually negative, which means the sine theta value is going to be negative as well. So when I go to here, I actually don't need to put the absolute value anymore. I can simply say this, and this is going to carry the negative value based on the fact that the y-coordinate of the point here was negative. Same logic with cosine of theta. Because the x-coordinate was positive, since we're in the fourth quadrant, when I go and do the cosine of angle theta, the x-coordinate of that point is also going to be positive, so I can drop the absolute value and do this. Then tangent of theta is simply sine of theta divided by cosine of theta, which is going to be y over x. Cosecant of theta is going to be the reciprocal of this, which is r over y. Secant of theta is going to be the reciprocal of cosine of theta, which is r over x. And then cotangent of theta, finally, is the reciprocal of tangent of theta, so we have x over y. So now we have a general way of finding the values of the 6 trig functions of an angle theta when the terminal side goes through a point somewhere outside the unit circle, and that's all the information we have. It's probably worth doing a recap of the quadrants in which each trig function is positive or negative. So first, sine of theta, which is the y-coordinate, is positive on the top half of the xy plane. So we would say sine of theta is positive in quadrants 1 and 2. Then sine of theta is negative in quadrants 3 and 4. Now, cosecant of theta is the reciprocal of sine theta. So wherever sine is positive, cosecant is also positive. And then wherever sine is negative, cosecant is also negative. Then, cosine of theta is the x-coordinate in the unit circle. So on the right half of the xy plane, cosine will be positive. It's quadrants 1 and 4. And then on the left side, cosine is negative, which means secant of theta, which is the reciprocal of cosine, follows the same pattern. Secant of theta positive on the right half of the unit circle, and secant theta negative on the left half. Then tangent is sine theta divided by cosine theta. So where sine theta and cosine theta have the same plus or minus sign, tangent of theta is going to be positive. Quadrants 1 and 3. Another way to think about it, remember, is it's y over x. So if you take the slope of the line, the slope is positive anywhere in quadrants 1 and 3, so tangent of theta is positive. And over here in quadrants 2 and 4, the slope is negative. That's where sine and cosine have opposite plus or minus signs. So tangent of theta will be negative. And since cotangent of theta is the reciprocal of tangent of theta, it'll follow the same pattern. Cotangent of theta will be positive in quadrants 1 and 3. Cotangent of theta will be negative in quadrants 2 and 4. So this allows us to use this information to identify which quadrant we're in if we are given certain values of the trigonometric functions. Now, let's consider a generic example problem where we're given some amount of information about the trig functions and we want to evaluate other trig functions. The easiest thing we can do is to sketch an xy coordinate system and say cosine of theta less than 0, that's negative, means we're on the left half of the xy plane. And then tangent of theta, which is y over x, or the slope, needs to be negative. So it's in quadrants 2 or 4. Combining that information, we know that we must be in quadrant 2. So if I draw a line segment, make a triangle, and say this is the angle theta, we can understand that tangent is y over x, or perhaps in the right triangle sense, we can think opposite over adjacent. So if I label this 1 and 3, then I can say this point is going to be negative 3, 1. Now, how did I know to put the negative on the 3? Well, it's because we're in the second quadrant, so the x-coordinate is negative, and the y-coordinate is positive. So the next immediate concern is to find the hypotenuse r. So we'll say r squared is equal to 3 squared plus 1 squared, which means r is the square root of 10. Then, to get sine of theta, we would say, oh, that's going to be the y-coordinate divided by the hypotenuse, opposite over hypotenuse. So we would say sine of theta is equal 1 divided by root 10, which we can rationalize, so say root 10 over 10. Then to get secant of theta, that's the reciprocal of cosine of theta. So I'm going to go ahead and write this like this, because it's more intuitively obvious to me what to do with cosine theta. That's going to be the x divided by the r. But keep in mind the x should contain the negative sign. So this should become 1 over negative 3 over root 10, which is going to simply be negative root 10 over 3. And there we have the values of sine of theta and secant of theta, just like this. Take the information, draw a picture, identify x, y, and r, and then find whatever you need to find. In order to justify the next thing we're going to discuss, I want to talk about something really cool. So let's imagine we have an angle theta whose terminal side passes through the point 15, 8. Now we can draw a triangle down to the x-axis. Note that the sides are 15 here, 8 here, and then do the Pythagorean theorem to find that the hypotenuse is 17. And we can use that information to say sine of theta is the y-coordinate divided by r, which is 8/17, and then cosine of theta is the x-coordinate divided by r, 15/17. And once we have those, we can find all the rest of the trig functions very simply. Now, the cool part is, what if I take this exact triangle and draw it into the second quadrant and make the triangle this way? So if I can make this more convincingly the same size, label the side lengths. This would be 15 here and 8 here. And I have the exact same triangle. The only difference is that when I go to label the point right there, I would label negative 15, 8, because the x-coordinate needs to be negative in the second quadrant. So then I ask myself, what is this angle? Well, if I believe that this theta has to show up right in here as well, then this angle in standard position would be 180 degrees minus theta, also known as pi minus theta. So then I could quickly say that sine of pi minus theta is the y-coordinate divided by the same r, which is going to be 8/17, and then cosine of pi minus theta is equal to the x-coordinate negative 15 over 17. Now, what if I took this and placed the triangle in the fourth quadrant? Same triangle, x-coordinate is positive, y-coordinate is negative. So what if I wanted, instead of going negative to make a clockwise angle, what if I wanted to go around counterclockwise? Well, I would say inside of this triangle, that same angle theta exists. So that means all the way around would be a full 360 degrees minus theta, also known as 2 pi minus theta. And then I could quickly say, oh, sine of 2 pi minus theta is the y-coordinate negative 8 divided by the same r, so that's negative 8 over 17, and cosine of 2 pi minus theta is the x-coordinate over the 17. So notice that we're using one triangle to generate the sine and cosine values at many angles other than the first one we used. But what's consistent is the angle theta inside the first triangle is the same angle theta inside each of the other triangles. This idea we are going to call the reference angle. So the reference angle for any angle in standard position is going to be the angle inside the triangle when you connect a point on the terminal side to the x-axis. We will call this the acute angle formed with the x-axis and the terminal side. All right, let's do some examples of this. Let's find the reference angle for 7 pi over 6 radians. Well, in the xy coordinate system, 7 pi over 6 is going to be a little bit more than pi. In fact, it might be easier if I take this and write this as a mixed number and write this as 1 and 1/6 pi, so I realize it's close to 1 pi. My goal is to find the angle right in there, which is the difference between the angle 7 pi over 6 and the negative x-axis, which is an angle of pi. So the easiest thing to do is just take the absolute value, 7 pi over 6 minus pi, because it takes the difference, and I get pi over 6. So the reference angle is pi over 6 right in here. Now what if I want to consider negative 9 pi over 4? Well, same logic. Maybe I should write this as a mixed number. That's 9 over 4 is 2 1/4 pi. So I'm close to negative 2 pi. XY coordinate system. Negative means go clockwise. So I'm going to go clockwise negative 2 1/4 pi. I'm going to end up down here somewhere where I've gone all the way around. And my goal is to find the angle in here formed with the x-axis. So since it's close to negative 2 pi, why don't I take the difference, negative 9 pi over 4, subtract negative 2 pi. Because if you take the absolute value, you get the difference. This is going to be positive 2 pi, so I'll get overall inside negative pi over 4. I'll write this down. Absolute value of negative pi over 4, which is simply pi over 4. this is the reference angle right in here. Now what if I do this in degrees? What if I say I want to find the reference angle for, we'll go with 312 degrees, okay? So if we take this and we say 312 degrees is going to be more than 270, we're going to be in the fourth quadrant, somewhere over here. We are now interested in finding this angle right there. I suppose I'll label this 312 degrees. So we understand we're close to 360, so why don't we just take the absolute value of the difference, 312 degrees and 360 degrees, which will give us 48 degrees. This is the reference angle for 312 degrees. Now, you might ask, how is this possibly useful? What if I want to evaluate, very innocently, sine of negative 23 pi over 6, but not using a calculator, just using geometry? So I think about a unit circle, and I want to know where the angle negative 23 pi over 6 ends up. Well, it might help to take negative 23 pi over 6 and rewrite it as a mixed number. It's going to be negative of 3 and 5/6. So I know I'm close to negative 4 pi. So that's clockwise, 1 rotation to get to negative 2 pi, almost 2 rotations to get to negative 4 pi. And I am very interested in finding that angle right there, the reference angle, so I can figure out what the x and y coordinates of that point are. So to find the reference angle, I guess I'll write this as reference angle, we'll take the absolute value of the difference between negative 23 pi over 6 and the closest multiple of pi. That gets us to the x-axis. So this is going to be minus negative 4 pi. That will come out to be positive pi over 6, and we know that in here, this reference angle is pi over 6, which then tells us that this triangle is going to have root 3 over 2, 1/2. So the x and y coordinates of the intersection with the unit circle are those values. So then we can immediately say, oh, then sine of negative 23 pi over 6 is just 1/2. Now let's imagine we want to evaluate something more interesting, like this. First, let's find sine of 4 pi over 3. We'll draw the xy coordinate system and say 4 pi over 3 counterclockwise is 1 1/3 pi. So it's 1 pi and 1/3. And we want to know, if we make this triangle, what the reference angle is. Okay, so the reference angle, we're going to take the difference between 4 pi over 3 and the nearest pi, which is 1 pi. Take the absolute value, that gets us pi over 3. Okay, so this is pi over 3 right in here, which means we know this triangle. It goes 1/2 to the left, root 3 over 2 down, and it has a hypotenuse of 1. So the x and y coordinates will be negative 1/2 because we're going to the left, negative root 3 over 2 because we're going down, and we can find sine of 4 pi over 3 by looking at the y coordinate divided by the hypotenuse. So this is negative root 3 over 2 divided by 1, which is just negative root 3 over 2. Okay, same logic with the cosine. We want clockwise negative 1 5/6 pi. So that's almost negative 2 pi. Clockwise, almost 2 pi. Okay, so then we're going to say the reference angle is going to show up right in here. That's the dot. And we're going to take the difference between our angle and the nearest pi, which is negative 2 pi, take the absolute value. This is 12 pi over 6, which comes out to pi over 6 overall. So the reference angle, pi over 6, tells us that the sides of this triangle are root 3 over 2 to the right, 1/2 up, and 1 for the hypotenuse. The coordinates of this point, root 3 over 2, comma, 1/2. So to get the cosine of negative 11 pi over 6, we would simply say the x coordinate divided by the hypotenuse is root 3 over 2. Then the final step, to actually evaluate the expression we were given, sine of 4 pi over 3 minus cosine of negative 11 pi over 6, is, the first one is negative root 3 over 2, and we will subtract another root 3 over 2, which will get us negative root 3. And that is the value. Let's check with a calculator and see if we agree. So I'll change to radian mode, and I will type in the original expression, sine of 4 pi over 3 minus cosine of negative 11 pi over 6. That is a decimal value. Just to check, I will take the negative of square root 3 and see if it comes out. We have a match. That is how you deal with these angles. So a very key point is, going forward, we're going to be dealing with a lot of different angles. Our goal is to, number one, recognize which quadrant it's in, as in which part of the xy coordinate system. So we want to use this idea of reference angles and locate ourselves based on the nearest pi and whether we're negative, positive for the y coordinates and the x coordinates. Once we've done that, we can rely on information we have, perhaps the 30-60-90 triangles, perhaps the 45-45-90 triangles, or perhaps something else given in the question. And then we just manipulate the x's and y's to our heart's content. And that's all. It's not that bad once you get in the hang of it. Well, thanks for tuning in, and hopefully the problem sets go well. And good luck. I'll see you next time.